Hi everybody. Hello, welcome back from spring break. I hope that many of you did something interesting and pleasant. Danielle got married over spring break. And maybe somebody can top that, but I doubt it. Okay, I think you all got email from me about ordering the book that we're going to use starting in about a week or 10 days. It's by David Christen. It's called This Fleeting World. And we actually have the publisher here. Karen, would you stand up? She's the publisher of David's book. And yeah. Okay, so she has a publishing company called Berkshire Publishers, which is actually doing a lot of things on big history. So it's good to have you here. I have a sign-up list here for you. I would urge you. I won't require that you buy this. I will get a couple of copies and put them on reserve. But if this isn't, if the $12 is something you can handle, do get this book, because it's one you ought to have in your library. You should be building up a list of the really critical things that you ought to be able to go back to. So I'm going to pass this around. Please make sure everybody says, "Oh yeah, here's the book." You see, it's not a big book, but it's really, it's good. It's good. Okay, make sure everybody signs that. Okay. All right. On Thursday before spring break, I gave you the update on Libya. For those of you who just come in, we've been looking at Libya because what's happening there is so historic, and nobody knows what's going to happen there, but it's unfolding before our eyes, and historians will find it interesting in the future. But on the Thursday of a week ago, I think you probably could tell that I was kind of depressed about the situation, because Gaddafi's army had moved all the way across to Benghazi in the east, and they were just about to go in, and it was quite clear that what was going to happen was going to be torture and murder on a very large scale. And the Western powers were seemingly doing nothing. Well, maybe you followed this, but the day after our class, NATO, together with the Arab League and with the authority of a UN resolution, decided to go in and do something. And after they basically dithered around for 2 weeks, at the very last moment, they got it together, and so there is now a no-fly zone. Did anybody hear the president's speech last night? Anybody hear that? Last night, President Obama gave a speech in which he explained what was going on. And from the standpoint of a historian, I found it absolutely fascinating, because it's clear that nobody knows what's going on. And this is so typical of the way history unfolds. In the future, 10, 20 years from now, you'll be able to read books about this, and you know exactly what was happening, and it will seem to you like everything was clear. But remember, we're in this situation of a fog of war right now. So let me just quickly shift over here to the other one. Okay, so quickly show you what's going on here. There. Okay, so here's Libya. And remember that the rebels are in control of the east. Gaddafi is in control of Tripoli, and he's also has a great support here at Sirte, which is his home and the home of his tribe. So that seems to be a Gaddafi support thing. So the situation is that right after the demonstrations and the revolt started, the rebels got all the way across to about here and did not get as far as Sirte. And this is a ragtag army, folks. This isn't an army. This is a ragtag bunch of people with guns who are trying to take over. They have basically no military training. So when Gaddafi decided to send his army eastward, they just rolled up the rebels real quickly. And so having gotten about as far as here, the rebels were pushed back through these two oil refinery towns, back through here, back through there, and all the way up to Benghazi, and that's where where Gaddafi's forces were just about to put an end to things when the UN resolution went into force. And so the point of the purpose of the UN resolution was to protect civilians, and it's really unclear. That's a vague thing. So how do you protect civilians? Do you only take out tanks and aircraft that are about to bomb a civilian area? Or do you take out their supply lines? It's being interpreted in different ways by different countries. And Gaddafi has no air power left. It's all been taken out. Quite a few tanks have apparently been taken out. And Gaddafi has been pushed or his people have been pushed all the way back here. So these are updated. This one is back in rebel hands. This one's back in rebel hands. So is Ras Lanuf refinery. So is Bin Jawad. And this is the place where, as of last night, there was fighting going on between the two sides. And what the rebels would like to do is to get over here to Sirte, which is Gaddafi's home. And nobody has any idea what's going to happen when they get there. You know, presumably this ragtag army is going to be able to go across there and at least knock on the doors of Sirte. And we don't know how strong Gaddafi's support is there or what's going to happen. Yes?
I literally driving over here was listening to the computer.
Oh, what's the latest?
The latest is that the rebels have been pushed out of Bin Jawad and Ras Lanuf.
Pushed back by Gaddafi. Yeah, I saw something that was sort of hinting at that this morning. So it's back and forth. Nobody knows what's going to happen, but from the historical standpoint, I thought it was interesting to look back. This is almost a replay of something that happened in 1940 to 1942. So let me get rid of these modern things here and just briefly tell you what was happening. So in 1939, Hitler in Germany invaded Poland up here and Czechoslovakia, and the Second World War began. And the French and British, who were the primary groups who were opposing Hitler at that time, were not able to do anything in Europe. Basically, Hitler just overran Europe very rapidly. And the fighting in 1940 and 41 really moved to North Africa, and the reason for that is that at that time this was an Italian colony and Egypt was a British colony. And so there was British army here, there was Italian army here, and so the Italians from here attacked the British in Egypt. And the obvious thing they were after was the Suez Canal, which is right here, because you see, let's zoom in on the Suez Canal for just a moment. Okay, it's right here. You can see it running along there. And that is the way that you get from the Red Sea to the Mediterranean. So look at what that means. If you have control, if you're the British and you have control of the Suez Canal and your main colony is India, look how easy it is to get to England like that. If you don't have control of that, you have to go all the way around here. So it was an obvious strategic target. So in 1940 then, the Italians attacked the British here, and the British counterattacked and were very successful, pushed all the way back into here, at which point the Germans, Hitler sent a very skillful tank commander whose name was Erwin Rommel. And maybe you've heard of the Desert Corps and Rommel's Desert Corps. And so they came in from this area and moved back, and they pushed the British back across there, and then finally the British were able to come back here. So they were back, forth, in, or no, forth and back in the desert. And there were huge tank battles there at the time. It was an amazing thing. And when Millie and I lived in Libya in the late 1960s, the results of that war were still all over the place. If you went into the desert, you were risking being killed by landmines that had been planted 25 years before. And if anybody would like, I have a fascinating map here. If anybody would like to come up afterwards, we'll open it out and see. But this is an oil company ordnance hazard map. Ordnance means military, bombs and things like that. So this shows where the minefields were and how you got through them. And so if you're interested in these things, come and see it. But it's really interesting to me right now to see the back and forth going on between Gaddafi and the rebels, sort of mimicking in miniature and more rapidly what happened there in the Second World War. There's a famous quote by Marx. I don't think anybody knows exactly what he meant, but he said that history repeats itself twice. First as tragedy, and then as farce. And I think there ought to be some way you could tie it into what's going on now, but I'm not quite sure. So that's the update on Libya. Keep following. If you would like to hear what the president said, I'm sure you can find it on the web and look at it. I was talking with Ryan and David about it and saying that I really liked that speech because it was like something a professor would give, but I'm not sure that it was exactly what the rest of the country wanted to hear. But if you read between the lines in that and listen between the lines in that speech, you will get this sense of who knows how this history is going to unfold. Okay? All right, let's talk about something else. There we go. Okay, so we're about to move into talking about human history. We've talked about cosmic history, we've talked about Earth history, life history. Now we're going to move into us. And things are getting complicated. And I think you all realize what a complicated world you live in. Do you ever have to deal with the administration of UC Berkeley? Okay, it's complicated, right? And imagine what it would be like if you had to deal with the whole state of California. If you were Governor Brown right now trying to run this huge, enormously complicated state, or the whole country, or the whole world. Just think about it and how intricate and complex everything is getting. David Christian makes the point, and other big historians have echoed this, that if we tried to find one really clear trend in all of big history, maybe it would be the trend towards increasing complexity. If you're wondering what complexity is, then you're in good company, because I don't think any of us know how to define it. I think everybody has a gut sense of what complexity is, but it's proven to be extremely difficult to define and to analyze and to understand. So what I want to do with you today, and this is almost for fun, is to take you on a tour of one kind of complexity. And it's not going to be historical complexity, it's going to be mathematical complexity. And some of you, I'm quite sure, have seen fractals. So I'm going to show you some fractals, and we're going to think about them as a kind of complexity which may or may not have something to do with historical complexity. But at any rate, as something you should know about. If you haven't seen these, you're in for a real treat. All right, so let's start here. And first of all, let's just think about the complexity of human beings and human society. So this is a crowd in the evening in St. Peter's Square in Rome who have come to hear the Pope speak about something. And when you look at this, thinking about it with the a historical mindedness that we've been trying to cultivate, just imagine all of the historical stories that are behind what's going on there and how complex and intricate all the relationships are. So we'll come back to that, but this has to do with complexity in history. And so what I want to do is show you instead something about complexity in mathematics. So let's make the point that there might be, this is a question really, is there some sort of natural law that requires increasing order or increasing complexity? Remember David Christian's notion that increasing complexity is the most pervasive through-going trend in all of big history. Is that just a chance that things get more complicated, more complex? Or is there some law that's driving it? I think there must be, but I don't know. And so for the physical and biological systems that underlie history, nobody knows. There are people who are trying to find out what this law, this hypothetical law of increasing complexity might be, but nobody's found out yet. But for mathematical laws, we do know, or for mathematical situations, we do know that there are very, very simple laws that can produce complexity that is absolutely amazing. Really incomprehensible complexity, and they come out of the most simple laws you could possibly imagine. So keep in mind, I'm telling you something that may be analogous to history or may not. We just don't know at this point. All right, so I want to look at some examples with you. Okay, and some of you will know about these. So let's look at fractals and read some of this to you just so we're on the same line. So a fractal is generally a rough or fragmented geometric shape that can be split into parts, each of which is at least approximately a reduced size copy of the whole. And this is a property that's called self-similarity. How many of you are at least somewhat familiar with this stuff? Okay, about half. That's good. Okay. That'll be perfect. So the term was coined by Benoit Mandelbrot in 1975. He's a French-born mathematician and was derived from the Latin fractus, meaning broken or fractured. And so a mathematical fractal here, I'm going to reiterate this to you a few times, but a mathematical fractal is based on an equation, usually a simple equation, and the importance is that it's nonlinear. That means it has some squared or high. It's got an x squared or an x cubed in it. That's critical. It's got to be nonlinear in that sense. And that equation undergoes iteration. So iteration means that you take your equation and you take a starting number and you run it through and you see what you get. And then you take that around, you put it back in the equation again. You run it through, take the result, and go around and around and around. That's called iterating. So what has been found out about these mathematical fractals is that you get them if you take a simple law, which is nonlinear, and you iterate it. That's all you need. And it's just amazing what comes out of it. So let's look at these. So let me give you some geometrical examples without the mathematics. So in this case, supposing that you start with a triangle, okay? And we're going to make up a rule. This rule is going to be like the equations we see later. This rule is going to control what happens. And the rule says anytime you have a straight line, we're going to take that straight line and divide it into thirds, and we could put another little triangle thing on top like that, okay? So here's one straight line. It's going to happen to that. Here's another straight line. Here's another straight line. Each of those is going to be replaced by this and filled in color. So you can see what happens. There it is. So see this, here's the original, and that's the original right there. So this side has been replaced by that. See how that works? So at this point, you've gone from a triangle to a Star of David, but now we can go and we can take each one of these. We'll take this one and replace it, okay? Got that, okay? Where do you stop? Well, you don't. You keep on going and going and going, okay? And this thing is called a Koch snowflake after the guy who first pointed it out that this happened. That's not terribly exciting, is it? It's sort of neat, but wait till you see what comes next. I mean, this is neat by comparison with nothing, but wait till you see the next ones. Okay, so let's take this one. We're going to start with a square now, and the rule is going to be that this is going to become that. So this is kind of a bit more complicated than the previous one. See how it happens? So picture in your mind, if you can, what this is going to be look like being replaced by the next one. Well, here's what it looks like. That's pretty neat, isn't it? And you can see the original one in there. Remember, that's what a side becomes. But the original one goes like this, 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 this. That's the original square. And now it's been turned into this thing. And now for every single one of these little guys in here, we're going to replace it by that. Okay, now we can go further. And I need a bigger drawing. It's sort of outlined there where you can see where it's going to be. Now that's pretty complicated, isn't it? Geometrically, it's complicated. And we did it with a simple rule, and we iterated it. Okay, so that's a kind of a hint where all this is going. So now let's take another one. Let's take this one, and instead of doing instead of taking a line and replacing it by a complicated line, now we're going to take this area here, and we're going to replace it by something else. So we're going to replace it by that. So what this says is that every time you have a square, you're going to just take the center out of it. So now you see this here was a square, so here's the square with the center out of it. Here's another square, and so forth. Okay, that one looks kind of neat, doesn't it? But still, it's not complicated enough for our taste, so we'll go to that. And then let's take this and turn it into 3 dimensions. So that's the result. So that whole thing, which if you set out to build that in your in the students' workshop in the architecture building or the physics department, it'd take you a long time to build that thing, wouldn't it? And it would be really hard to get it accurate. But the whole thing is generated by the simple rule that says if we take a square, we replace it with a square with a hole in it. All right? So that's the beginning of fractals. And remember, fractals have something that's called self-similarity, which means that no matter what scale you look at it, you're still seeing something that looks sort of the same. So, you know, you can see that this one sort of looks like that one, only more intricate. And this one, so that's self-similarity. So we'll come back to that. Okay, so here are trees that are made by a simple rule, iterated. And the rule clearly says that every time you come to the end of a line here, you replace it with a little V like that. And you come to the end of that line, you replace it by a V. And this one, you replace it by a V. And by doing that simple little thing, you get this tree, and you can get different shaped trees by just specifying the angle. The only thing that's different about these is that this angle is wider here and wider still there. Another thing you've got to put into here is that at the end of the length, a line of this length, you put a line that's a little bit shorter and a line that's a little bit shorter. So what possible value or use does this have in understanding anything other than that mathematics has some neat stuff in it? Well, when you look at these and you see a tree, it makes you wonder, is the tree genetically programmed to produce something like this? When you come to the end of a limb, you start 2 more limbs. If you watch a tree in your yard growing, you know, year after year, you can kind of see this happening. So probably real plants are running something like this program in order to generate the pattern that you see. Okay, and what Mandelbrot and other people found is that with fairly simple rules, you can generate these things which are really quite beautiful, very ornate, and you know, it's hard not to look at that and say, you know, that's really pretty. So there are books now, and find one in a library, or find this stuff online is probably what you do, and just look at fractals and see all the fabulous fractals that have been discovered. Many, many have been discovered, and we're going to look at 2 quite astonishing ones in a moment. But it's even been applied to landscapes. This is not a mountain range that ever existed. This is a mountain range which Mandelbrot generated by figuring out some fairly simple rule And I don't know what the rule is, but anyhow, this is a mathematically generated landscape. And what he found was that when he changed his rules a little bit, he got either landscapes that look more realistic or less realistic. Or to a geologist looking like me looking at that, that's probably a volcanic rock as opposed to granites or sedimentary rocks. And of course, it's none of them. It's just a mathematical construction, but still, it's fun, right? Okay, so now I want to take you to see the first. Oh yes, okay. Yeah, man.
With these landscapes created by fractals, is that caused by some natural phenomenon that has similar properties to the simple equation that's used to generate them? I mean, is there something going on that's just like on a really small scale that's being repeated again and again?
Yeah, that's a profound question, and I don't think there's an answer to it. I will say that there are some geologists who got really excited about this when Mandelbrot's work first came out, and they started trying to figure out how can you use fractals to make sense of things in geology. And there's something called a fractal dimension, which I may talk about later, but anyhow, it's a characteristic of this. Let's just go back to the one you were pointing at. Okay, so if the fractal dimension was a little bit higher, this would be more jagged. And if it was lower, it would be smoother. So what people have done is to look at all sorts of landscape features and geological features and calculate what the fractal dimension was. Sadly, it hasn't gone very far from that. It isn't clear what you can do to increase your understanding by knowing the fractal dimension. So at this point, nobody's figured out what to do with this, and maybe somebody will, but I hope that's a good answer to your question. Yeah, Michelle?
It was actually a similar concept.
Okay.
But, I was wondering about beforehand when you talked about snowflakes, I was wondering if anybody has analyzed sort of the crystal repetition and how that, it's a similar.
Well, there's a difference because crystals are extremely regular. You know, all the atoms sit in exactly the same point. And so they aren't fractal in this sense. They're you know, people who think about these things think about all sorts of regularities, and the crystals can be really, really regular. And then these things, well, like the pretty sort of circular thing that's not regular, it's intricate. But yes, yes.
I'm not sure about the landscape of the circle, but the other ones would be really interesting to use gratitude to keep going and see like ends.
Yes, and we're going to do exactly that. That's exactly what people think. So if you want to find this stuff, Mandelbrot, look up Mandelbrot set zoom, and in fact I think there's even someplace here and there's something about it. But I'm going to show you one of those because that's very perceptive. That in fact what we find is that the complexity goes on and on and on to infinity. Some of these things are infinitely complex and much more interesting than those very regular ones that I showed you at the beginning. Okay, so I'm going to show you now two really cool fractals. And the first one has to do with something that's called the logistic equation, which is a basic equation that people use in ecology. So here's the point, and I'm not going to go very deep in this, but I want you to see enough of it to understand what's going on. So one of the first examples of chaos and fractals, chaos is another word that we're going to build in here in a moment. They came from a surprisingly simple equation called the logistic equation. So it is important in ecology, and it considers the question of how a population of organisms will grow through time. So let's see how it works. So imagine that in some area you have a population of insects of some species. Let's say, supposing there are 100 of them in this, you're doing this maybe in a laboratory and you've got a nice little place for insects to live. And you start with 100 insects. And then they reproduce. Just to make it easy, we'll say this species of insects reproduces once a year with a new generation appearing and the old one dying off. I'm seeing the first spiders coming out, and they do that. And the spiders, they grow all year, reproduce, and then the whole generation dies off and a new generation appears. So something like spiders, okay? And now, suppose that the population increases by 50% each year. In other words, if you have 100 spiders this year, you have 150 next year, okay? How many insects are there in each successive generation? Okay, anybody here who's in math or statistics or physical science, biological science has probably already done this. If you're good at that, you can derive an equation. It's going to tell you the population for any given generation number. Say, remember, we start with 100 insects. After each year, there's half again as many. 150, and then half again as many. You can write an equation, which we won't bother doing, that says after the 43rd generation, how many insects are there, right? That's going to be a whole lot. But nature doesn't do it that way. Nature does it by iterating, by saying, okay, we start out with this many insects, and they mate with each other, and we get 1.5 times as many, and then they all mate with each other in the next generation, and so forth. So let's not do it by writing the equation for it, or by this equation. Let's do it by iterating. So let's see. Here's how we're going to do it. Iterating means, remember, cycling through the equation again and again and again. So what we're going to say is we're going to multiply the insects by 1.5, the number of insects. That gives you a 50% increase. Then we'll take the result and multiply it by 1.5 again and again. So here's how we're doing. Remember, we started with 100 insects. We'll call that population X1. That's the number of insects in generation 1. Okay, so then what we do is we go over here, and X2, which is the number in the next generation, equals that 100 times 1.5, which is the increase, and that gives you 150 insects. And then in the iteration process, we take that over here, and that's X2, and the number in the third generation is that times 1.5, that's 225. And the third one, 338, and so on. After 10 generations, you've got 3,844 insects. It's getting crowded, right? After 40 generations, you have 737 million insects. And after 41 generations, you've got 1 billion insects in this little box. I hope it's a big box, right? And this started with 100 and just multiplying by 1.5 each time. And so if you go down here, and you go down to X, I don't know, the 60th generation or the 100th generation, basically you have the entire planet covered in insects stacked millions deep, right? Is this a reasonable picture? In ecology, is this going to happen? It's not going to happen, right? Something has got to give. They can't keep on multiplying and increasing at that rate indefinitely. So the logistic equation was set up to figure out what really happens. So what do you think happens? Once it gets really crowded in that box, what happens? What happens to the reproduction rate? It's going to go down, sure. They aren't going to keep being able to increase at that rate. And if you're wondering whether this might have something to relevance to our situation on this planet, well, it probably does. Yeah. Okay, but let's see now how they figured out how to deal this. So obviously insects cannot increase their population indefinitely, nor can any other species. There's going to be a limit called the carrying capacity. That's basically how many insects can fit in your box that you started with 100 in, okay? All right, so then as the population gets closer to that carrying capacity, supposing that the carrying capacity is 1 million, you know, as you start to get to 800,000, 900,000, getting closer and closer, something's going to happen, and the reproductive rate's going to have to decline. And in our case, remember, it started at 50%, and it's going to have to get lower and lower. So the logistic equation takes care of that in a very neat way. So let's call that carrying capacity 1. As physicists say, we're normalizing to 1. So you can think of it as 1 carrying capacity full, or 1 whole carrying capacity, right? So if the carrying capacity happened to be 500,000, then a population of 250,000 insects is 0.5. It's half of that 1. You see how this is going? Anybody got a question at this point? Okay, so the trick then, or what's going to happen, is to have the reproductive rate and we're going to call that R, you have to have it decline as the population approaches the carrying capacity. And so they figured out a nice simple model that would do that. They're going to adjust it. So the adjusted reproductive rate, remember the original rate was R, that was 1.5. So now as you get closer, as this population here gets closer and closer to the carrying capacity, you subtract it from 1. So this number gets smaller and smaller and smaller, and therefore R gets smaller. See how that works? Okay? So now, let's see, how did I do that? So then you can keep iterating, and you'll never get past the carrying capacity. But here's the neat thing. We can say that this is going to be the number of insects in generation after the one we're interested in. So this is the one we're interested in. This is the number in the next generation. So it's going to be R times X, which is what we did before, but then it's got this 1 minus X, which is going to reduce that reproductive rate. All right, so here's the point. You can go back through all this and look at it. It's pretty simple, but the point is that the final equation you get here that you're going to iterate through is that the new generation has got an x squared in it. Remember, it's these two together. So the point is it's got an x squared, and this is critical. This stuff that we're going to see only happens when you have a nonlinear equation that has an x squared in it. Okay, so hopefully you think this is mildly interesting, and now I want you to all wake up, because it's going to turn out that it's more than mildly interesting. It turned out to be the key to one of the truly great and completely astonishing discoveries of all time. So let's see. Yeah.
Is this just in theory, and if not, how does that actually play out biologically? What do we know, or how does our biological systems kick in order to make that come to fruition?
Well, I think the way it kicks in is that if you're getting close to the number of the carrying capacity, animals get less and less to eat. It's harder and harder for them to eat, and therefore they're going to die before they can reproduce, and that means the reproduction rate. That's a really good question, by the way. But yeah, I had to think fast about that. But I think that's the answer to the question, right? So that's how it plays out. Yeah.
There's also, when you have a larger population, there's more waste that's created. So,
More waste?
Yeah.
Yeah. Uh-huh.
So that contributes to death.
Mm-hmm. Mm-hmm. So all sorts of various ways. And so this is a mathematician's way of thinking about what's a biological problem. And it turned out that the mathematician's way led to this incredible discovery. So let's look at it. So what we're going to do is to explore the results of the logistic equation. Now, I've put an Excel spreadsheet onto BSpace. It's under today's thing. And this is the name of it. And it's going to let you explore. And let's just explore it together. So what we're going to do is we're going to iterate a nonlinear equation. Nonlinear because it has a squared term in it. And iterating, which doesn't seem like a very big deal, and having an x squared in it, which doesn't seem like a very big deal, are going to lead to this incredible complexity. So let's look at it. So now I'm going to get out of here for a moment and go to this spreadsheet. Where is it? There. Okay, let me show you. This, as I say, you can play with this. And let's see. What's in it? Oh, okay. I see. That's what I need there. I need this a little bit bigger. Hold on a second. Okay. So here's what's going on. Remember, R is the reproductive rate, which we started out with it being 1.5, which meant half again as many each time. And so here is that rate up here, 1.5. And then you also have the number of insects you started out with. And remember, we started with 100. But I'm going to sort of generalize right now, and I'm going to put over here the reproductive rate, in this case 3.6. That means when you started with 100, you have 360 the next time around. And over here, N0 is the number that you started out with, and that's going to be a fraction of the carrying capacity. So if the carrying capacity was 1 million, this carrying capacity is 400,000. But what I want to do now is to start on a different number, and I really should have put this one in here to start with. I think 2.5 will do. Did that go in there? That's the wrong place, excuse me. That's not what I wanted to do. I wanted to put it here, 2.5. And now, look what happens here. So this means you started with 0.4, 4/10 of the carrying capacity. That's how many insects were there. And they reproduce at this rate of 2.5 times as many each generation. And what happens is, there's where you start, and you jump up here. This is the next generation, and it happens to be at 0.6, and it turns out that that is what they stay at. So you iterate it again and again and again and again, and every time there's a balance now. So this is a stable population. Every one has 6/10 of the carrying capacity. Is this clear to everybody? Okay? And this isn't very exciting, is it? No. Okay, so let's go on, and now instead of 2.5, I'm going to say, what happens if your reproductive rate is 3? So there's 3 times as many as there were. Okay, let's see what happens. Oh, now this is kind of interesting, isn't it? So what's happening here, remember this says iteration number across here, and you can think of that as being which generation we're in. So here you start at 0.4 of the carrying capacity, and the first value goes to here, and it overshoots. There's too many. So the next time around, there's fewer. And then there's not as many as there could be, so there's more. So the population is jumping back and forth again and again, and it takes a little while to stabilize. But by the time it's over here, what you see is that for this number of starting insects and this reproduction rate, you bounce back and forth, and like that, between larger population, smaller, larger, smaller, larger, smaller, and so forth. It goes on indefinitely. Yeah? And the term that the mathematicians use for this is period 2. Back and forth 2 times. Okay, so let's go on to another number here. And instead of the reproduction rate being 3, I'm going to make it be 3 point, and these numbers are in the lower corner, 44949, 949. And now let's see what happens. Oh, so it started out here, jumped up there, and it's cycling back and forth, so that each generation is different from the number in the previous generation, but it cycles through, and every 4 times through it repeats. Okay? So this is called period 4. So what happens next? Yeah?
Is it dependent on like the energy needed to sustain the populations being consistent?
In the real world, yes. We've now shifted to mathematics. We're just simply looking at what happens when you take a simple nonlinear equation and iterate it. So at this point, you should stop thinking about animals or insects and start thinking, this is a property of mathematics. Okay? Okay, so you see here it repeats every 4th time. It takes a little while to sort of stabilize, but over here it's 1, 2, 3, 4. This may look like every other time, but actually it's every 4th. So now we can go up to the next one here, and instead of this one, we can put in 3.5. I think I did that one. 4, 5, 6. I can hardly read that. 4407. 7. Okay. And I really urge you to do this yourself later. Now what you get? Okay. Well, it turns out that one repeats. There's a pattern that repeats after every 16 generations. And so I think you would be justified in imagining that every time we increase the reproductive rate by a little bit, we're going to double the number of generations. Huh? We'd go from period 16 to period 32 to period 64 and so forth. Is that right? Wrong. That's not what happens. What happens, and this is the discovery, and I think can I read it down there? 3 point, and you can explore these for different numbers. I've just written down numbers that I found useful myself. Let's see there. It's hard to do this on here. 3 point, I can probably read it here, 56994, 567, I hope this is going to work. It didn't earlier today, but so remember, this means if you start out with 100 insects in the first generation, the second generation has 356, right? Something like that. Okay, you ready for what's going to happen? I hope it's going to happen. Oh, shoot, that's not it. Did I get that right? 3.56994567. This happened this morning. I can figure out why. That is not what I'm looking for. Let me go to a little bit higher number here. Let's go to 4 just to see what happens. Okay, that's it. Now this is not regular, right? This is the great discovery. This is something that's called chaos. It's called deterministic chaos. And it's deterministic because if you make the spreadsheet and put in the same numbers I did, you will get exactly the same pattern I do. It will not differ. It's absolutely controlled by the mathematics behind this. There's no room for anything to change if you put in the same numbers I did. Okay? And yet it doesn't repeat. Okay, now here's a really amazing thing about this. This is called chaos in the technical sense. And what happens on this is if you change one of these numbers by a little bit, at least the last part of it is going to diverge. So now, what I'm going to do is I'm going to change this 4 up here to some number like 4.001 or something like that. So now that means that the reproductive rate is changed by a tiny little bit. And now what happens to the pattern? And this is the number of insects in each generation. Now especially watch the right-hand side of the graph when I change this. Did you see? Well, in fact, the whole thing changed, didn't it? Let me go back, and that's the way it was. And so that changed the whole thing. So now what I'm going to do is I'm going to change it by a very small amount, 4.0000001, something like that. Maybe that will only affect the right-hand side of the graph. Now watch this. Did it happen? I hate it when this stuff does this. So there we're on 4. Why is this not working? 4.00001. Now that should work. Watch the graph. There. And that changed the whole graph. What I'm trying to do is to get one over here that only changes the right-hand side of it, 4.0000001. So you see this number is different from the previous one by a tiny, tiny, tiny little amount. Basically an indetectable amount in nature. Now watch and see what happens. There. I don't know if you could see it, but this side stayed the same and all of this changed. Okay, I'm not going to belabor the point too much more except to say this. When you're dealing with mathematical chaotic systems, the starting point that you put in determines the ending point, and even the tiniest little difference in the starting point gives you a completely different result after many iterations. So there's a name for this. It's called sensitive dependence on initial conditions. Sensitive dependence on initial conditions. So in other words, if you change the starting point, the initial conditions, ever so slightly, in the end you get a completely different result. Yeah, somebody... Yes, yes.
Is there any relationship between the numbers that create like an even period and the ones that come to chaos?
Yeah, people have, the question is, what about the boundaries between period 2 and period 4, and what about the bound?
Will it go higher than 4? Will it go back to being like evenly spaced?
I'm going to let you explore that, but in fact, those numbers, the boundary numbers, turn out to be fundamental constants of mathematics, and people have worked out the most amazing things about how they're all related. Okay, so now let me show you how this works out, I guess I want to go back to the PowerPoint, and let's try to do this right. Okay, so we've explored that. I do urge that you explore it. I hope it works better for you than it's worked every time for me. Okay, so now this is a plot of the logistic equation. Let me show you how this works. Okay, so this is going to be the reproductive rate across here. Remember, we started out with it being about 2.5 somewhere, and then we went up. And when we got to around 4, funny things were happening. So when we were in period 2, remember, you basically jump back and forth between the population that's too large and the population that's too small. So here are the two. Basically what this means is that if you ran it through many, many generations, you would be back and forth between this value and this value, because this is the percent of the carrying capacity. Does this graph make sense to you? This graph you can't generate quickly. What you have to do is to take each value of the reproductive rate and run it many, many, many times. And then you find out here that it's this one or this one. When you get to period 4, you're at this reproductive rate, and it's a line up here, and it jumps back and forth between, say, this one, this one, this one, this one. This one, this one, this one, this one. And so these are lines across here because they're showing where those numbers are as a function of what the reproductive rate is. And then here, this is period 8, and then this is period 16, and this is called chaos in here. Because this is when we saw no regularity. And so what you see is that these things jump all over here, and what any one of these vertical bands up here would look like depends on exactly what number you choose for the reproductive rate. And so this is called chaos. And now let's think of it, let's change our way of thinking about it and think about it as a geometrical object. And if you look at it, it has this very characteristic appearance, like turned on its side, it's almost like this is a tree up to here, and then it's got branches, and then all of a sudden you get all of this vegetation in here. And this one, but there's strange things like this line here seems to kind of run through this section. And then as you keep increasing the reproductive rate number to higher and higher levels, you find yourself in areas that don't have this chaos. It leaves chaos. It goes back out of chaos into something that has period 2 and then period 4 and then period 8. And so if we take this whole area here and stick it there, I've sort of changed the shape as well. But this green box is the same as that green box. So this little feature in here is that one right there. So what you're seeing now is inside this band of order, there's a new little window of chaos appearing. And then if we take this one here and blow it up to this, here's what it looks like. And now you can see that there are new little bands of order appearing, and each one has its own chaotic. Isn't that an amazing thing? This came out of that simple little equation. X prime equals R times X times 1 minus X. And you just iterated. Nobody in the 19th century would ever have believed that stuff like this could go on, even up till the middle of the 20th century. This was an utterly fantastic discovery in mathematics. And boy, did it really upset mathematicians who thought that all of mathematics was orderly. Suddenly they discovered, no, folks, it ain't. You can have this weird stuff happening. Okay, so that's the logistic equation, and the point here is, I keep repeating this point, is that in mathematics, very simple equations and very simple rules, iterate, can produce enormous complexity. And so it may be that the complexity that we're seeing in history somehow works in the same way, that it's a simple rule iterated. I mean, we're one generation, there's going to be another generation, and so forth. Iterated again and again and again may lead to absolutely extraordinary and quite unpredictable results like this. So this is complexity. All right. So there, remember, this is what I was showing you before. There's period 2, period 4, period 8, and there's chaos. And then there are non-chaotic islands that each have their period 2, period 4, period 8. So that is what the logistic equation does, and it goes on. It's been proven that this goes on to infinity. You can keep going in this as close as you want, and it will still look like something like this. Okay, now I'm going to show you the most remarkable one of all, so take a moment and just refocus. Man, yeah.
Like
What?
the butterfly effect that's related to this?
Absolutely. It's the butterfly effect is an example of sensitive dependence on initial conditions.
Yeah, 'cause I
That's
saw a
ex-
video.
yeah.
I don't know if I emailed you this video a while ago. But it was just
Yeah,
like
I'm
this
sorry.
exact thing.
It is. It's neat, isn't it? Yeah. Yeah, Wes?
So that is once you're pretty much at theoretically what you're doing.
Will you ask me afterwards? I'm going to get started so we don't lose everybody, but do ask me later. Okay, are you ready to go? You ready to see the biggest one of all? Okay. So the graph of the logistic equation that we were just looking at seems to be telling us something profound about geometrical complexity, although it's not clear what it really means. But now let's look at something even more astonishing, and as you might expect, it involves iterating a nonlinear equation. Okay, this is the Mandelbrot set. How many of you know about the Mandelbrot set? How many of you have played with the Mandelbrot set? Oh, this is great. All sorts of people who haven't. You're in for a treat. Okay, here we go. All right, so this is an incredible example of complexity. You're getting tired of hearing me say this again, but here it is, generated by a simple nonlinear rule of iteration. Okay, now this is a map. So this is going to be a graphic, this is a visual that we can look at. And it's on the plane of complex numbers. I'm going to show you that in a moment because some of you have probably forgotten what that is. But at any rate, it shows what happens to each point on the plane of complex numbers when it goes through many iterations according to the rule that's specified, the nonlinear rule. Okay? So just a review of complex numbers, and this isn't critical to it, but I think it's probably value. And by the way, will you fix your hand out here? It didn't come out right. The two areas in circles are wrong. This one here on the handout should have a square root sign in it. And then that unreadable one in the upper right, you might put in the axes here and the line going out. That's an arrow up there. Just okay. Sorry that didn't come out. All right. So remember what complex numbers are. If you ask what is the square root of -1, the answer is there isn't any square root of -1, right? So we can imagine that it has one, and that's called an imaginary number, and it's called I. So that's the square root of -1, and so a complex number then is one that has a real number in it, like 4, and it has an imaginary number like 6i in it, where I is the square root of -1. And even though there isn't any such number, it turns out that in mathematics it's very useful to imagine that there is. You can do all sorts of stuff with it. And so then you can have a plane here, and this axis, instead of this being x and y, this axis is the axis of real numbers. So there's 2 and there's 4, for example. And this is the axis of imaginary numbers. So this might be plus 3i, and that might be minus 3i. All right, so most of you are familiar with this. Okay, so you can add. So there's what a complex number looks like: a plus b times I. So you can add them by adding those two, and you get 9. And here you get minus 2i. And you can multiply them, and you multiply them through. And the point is that here, that if you multiply minus 2i times plus 3i, you have minus 6i squared. But what is I squared? It's -1. So that it keeps kind of working back and forth. And you can square the complex number, and there's a distance here. The distance, if that's the complex number, the distance from the origin is done by Pythagoras, like that. And so review that if you want to, but it isn't critical. The point here is that when we think about the Mandelbrot set, it's going to iterate an equation, and we're going to have each point on the plane. Let me go back here. Remember, here's the origin, and there's a point called C, which is a plus b times I, times the square root of -1. Okay, so what Mandelbrot figured out to do was to say, well, here's going to be our rule. We're going to start with this number z, and we're going to start at the origin. The origin of the complex plane is 0 plus 0i. And then we're going to calculate z prime, which is a new one. We're going to iterate this. And here's the rule. Look at that. This rule is z prime equals z squared. It's got to have a squared in it because it's nonlinear. And then we're going to add the number that we, I always get confused at this point. For each point, okay, for this is the number for a point in the, okay, imagine this, you've got a graph, and it's got imaginary numbers, it's got real numbers on it, and we're going to start at some point there, and it's got it's got a coordinate in it, which is like 4 plus 6i, something like that. Okay, so that we keep that, and what we do is we start at the center, and we square that, and we add our number for our point, and we get a new value, and then you square that and add this number. And each time, this becomes a point where our starting point has moved to. This will be clear in a moment. And so then we can iterate it many times and see what path is traced out on the complex plane by these successive values. So look at that equation. You could write that on your palm of your hand with a pen right now, and you could remember that. That is a simple equation, but it's got a squared in it. So now let's see what happens. Okay, so we're going to look at the iterative behavior. What happens to each of those points on the plane as you iterate it through that equation. So the Mandelbrot set, is usually shown as black, is all the points that never go out to infinite distance. You can iterate them as many times as you want, millions, billions of times, and they never escape. Then there are points outside the Mandelbrot set, and they go to infinity. You iterate them through that equation a few times. Eventually it streaks off to infinity and it's gone and it never comes back. And what people do in dealing with the Mandelbrot set is they color code them. They color code the different places on the map to show how long it takes to infinity, to go to infinity, how many iterations it takes to go through. Okay, so let's look now and see what happens. So there's the Mandelbrot set. This has sort of become the icon for complexity. And you don't usually see it with the axes on it, but when you calculate it, you're doing axes. So remember, this is the complex plane. So this is the plane of real numbers. So this thing goes from less than +1 to out to about -2. And these are the complex numbers. So this is 1i, and this is -1i. So what we're going to do is take any point in here, inside or outside this thing, and we're going to iterate it through that equation again and again and again and see how long it takes to go to infinity, or maybe it doesn't go to infinity. So here, for example, there's one, and these aren't calculated, this is just to give you a general idea what it looks like. That one, if you start at that point, the first iteration takes it there, and the second iteration takes it far out, and it's gone real fast. So this one is way outside the Mandelbrot set. The Mandelbrot set is all of the points that are shown in black. And now what happens if you take one that is close to the edge of the Mandelbrot set, like this one? Then you iterate, and it jumps around for a while like that, but eventually it goes to infinity, but it takes longer to do that. And so this one is near the Mandelbrot set, but not in it. And then if you take one that's actually in the Mandelbrot set, it just bounces around in there forever and never, ever, ever leaves. So all the points that do this are shown in black, and all the points that don't do that, all the ones that escape, are shown color-coded to show how long it takes to go to infinity. How many, when I say how long, I mean how many iterations. Okay, so let's see now what happens with this. If you poke around in the Mandelbrot set and zoom in, and here's come back to zoom. Who was it who said, yeah. If you zoom in the Mandelbrot set, you find these incredible things in there. So this one, right here, I don't see anything black on this, so there's nothing in the Mandelbrot. We're entirely outside the Mandelbrot set, but it is color-coded, and I suspect that the dark blue ones get to infinity in fewer iterations, and the yellow ones take more iterations. But can you imagine that's in there? Remember the equation? That equation that maybe you wrote on your hand? This is generated by it. Can you imagine the sensation that was caused when this was discovered? Most mathematicians hated it, and everybody else loved it. Okay? So here's another one. Look at that. Okay, now this one is astonishing because we focused in on some tiny little place near the edge of the Mandelbrot set. But look at this little thing in there. Does that look like the Mandelbrot set itself? That's a miniature Mandelbrot set. And there's an infinite number of tiny little Mandelbrot sets at all sizes. And it's been proven that every one of them is connected by a little black line there. All the way down here is a thin little wisp that's all inside the Mandelbrot set, and it connects it. So all the little mini Mandelbrot sets are all connected to the big one. This is complexity, huh? You look like your head's spinning, right? Okay. All right. So there's another one and another one. Look at those things. And it's hard not to derive just pure pleasure from looking at those things, as long as you're not a mathematician, right? And it may be that down in there's a little Mandelbrot set buried. But remember, in these pictures, you don't know how far you've zoomed in. So let's do that. Let's take care and let's do that. Okay, so Roland has put these zooms into video. And these are, you can find lots of these on the web. There's the Mandelbrot set. Now what they're going to do here is to zoom in on some particular spot. And you can choose any spot you want to, and you'll find something. See, look at all the little Mandelbrot sets in there, all in black. Is that the end? It shouldn't be. And look at these fun. Doesn't that look like lightning strikes across there? Remember, we're not in the main Mandelbrot set. We're in a little subsidiary one. They've all got little Mandelbrot sets in them, don't they? The original Mandelbrot set is now probably the size of the state of California. And mathematicians have proven that this complexity continues on to infinity. You never run out of it. What do I do to move on, Roland? Just okay. So let me show you this one, because this one is a different version. I've never seen one quite like this, because they keep comparing it to things that we see in our world around us. Geodes. That's for you. Pardon me, I'm going to stop it right there. You can find that on one of those websites. But I did want to just bring this home and think about it for a moment before we finish. So here's a quote I love. What is this thing? The Mandelbrot set broods in silent complexity at the center of a vast two-dimensional sheet of numbers called the complex plane. When a certain nonlinear operation is applied repeatedly to the numbers, the ones outside of the set flee to infinity. The numbers inside remain to drift or dance about. Close to the boundary, minutely choreographed wanderings mark the onset of the stability. Here is an infinite regress of detail that astonishes us with its variety, its complexity, and its strange beauty. So let's think a little bit more about what it is, what it means to us. So the Mandelbrot set shows how in mathematics a simple law, iterative and nonlinear, can generate literally infinite complexity. There is no end to this complexity. Right? Now, iteration and nonlinearity are common in nature. I mean, one generation giving birth to the next generation and the next and the next. That's iteration. And it's quite clear that we are much more complicated than can be described by any linear equation. So this is a, the historical world we live in is somehow analogous to this mathematical thing. Could there be a more general law of nature which requires and specifies the growth of complexity whenever an entropy deficit makes it possible? So such a law would explain the complexity we see everywhere in oceans, atmospheres, organisms, ecosystems, in societies. And so few scientists are searching for that law. And I don't know whether there is one, but if it is, it'll be one of the great discoveries of all time. So the last thing I'd just like you to look again is at this picture that we started with of St. Peter's Square. And let me just show some of the things here that you can think about the complexity that is in this and historical complexity. So here's some things. For example, this is an obelisk that was brought from Egypt back to Rome. And so it tells you something about Egyptian civilization. We're going to see soon about people being driven out of the Sahara into the Nile Valley by drought to make that civilization start. Here is another architectural thing. These huge columns here with their capitals, they come from classical Greece, from Athens, right? And up on the top of the building are huge statues of Jesus and 12 saints, which reminds us of the influence of the Bible and of religion on all of the world we live in. Here's this huge dome that Michelangelo built on St. Peter's, which tells you something about the history of engineering. And here's the Pope's balcony, and this reminds us that the Catholic Church has strongly influenced history for 2,000 years, and other religions have influenced it in other ways. Here, for example, are travertine columns from a place called Tivoli near Rome. And we'll be talking about the volcanoes that are responsible for that soon. So that's the history there. And then just think about this. It's hard to read that. It says, each of these people is a linear descendant of the very first living organism on Earth. Each of them has a unique and complex genealogy, life experience, mind, and ideas. And each of them influences and interacts with thousands of other people. So as you see, we are really into the realm of complexity. And one last thing, it just reminded, I think somebody was doing a talk on fractals. And whoever that is ought to come up and talk to me, so that I hope I haven't stolen all of your good stuff. Oh, who is it? Jeff? Louis. Okay, I'll talk to him. Okay, folks, thanks.